Imagine staring into the night sky, tracing the twinkling dots of distant galaxies, each one a colossal island of stars, planets, and untold mysteries. But what if I told you those galaxies aren't scattered randomly? They're threaded together like beads on an invisible string, part of an enormous cosmic web stretching billions of light years across the universe. These filaments, the largest structures in existence, aren't just empty space. They're highways of dark matter, glowing with faint tendrils of hot gas and hiding secrets that defy our understanding of physics itself. And today, we're diving deep into 25 of the most mind-bending, unexplained phenomena lurking within these cosmic threads, phenomena that could rewrite everything we know about the universe. This isn't just a story about faraway galaxies. It's a puzzle that touches the very fabric of reality. Picture this: filaments so massive they could swallow thousands of Milky Ways, yet so delicate they're almost invisible. They shouldn't exist according to some of our best models, and yet there they are. Some glow with unexplained energy, others seem to bend the rules of gravity. A few might even hold clues to parallel universes. Every time astronomers peer deeper into these cosmic threads, they uncover something new, something that leaves them staring at their screens in stunned silence. So why does any of this matter? Because these filaments aren't just distant curiosities. They're the scaffolding of the universe, the hidden framework that shaped everything, including us. Without them, galaxies wouldn't have formed, stars wouldn't shine, you and I wouldn't be here to wonder about them. And yet, despite their colossal importance, we've barely scratched the surface of their mysteries. That's why this journey matters. Over the next 25 revelations, we'll confront cosmic riddles that challenge the limits of science, venturing into the unknown where even the boldest theories tremble. Are you ready to step into the shadows of the cosmic web? Let's begin. The cosmic web should be teeming with ordinary matter, the same protons, neutrons, and electrons that make up stars, planets, and even our own bodies. But here's the problem. When scientists tally up all the visible matter in the universe, nearly half of it has vanished without a trace. This is the Missing Baryon Problem, one of the most stubborn puzzles in modern cosmology. Where did it go? The leading suspect, the very filaments we've been exploring. For decades, astronomers assumed this missing matter was hiding in the vast spaces between galaxies, perhaps as a diffuse, superheated gas too faint to detect. Enter the warm, hot intergalactic medium, WIM for short. Theory suggests these filaments should be laced with it, a thin but searing plasma hotter than the surface of the Sun, stretching millions of light years between galaxy clusters. The trouble: spotting WIM is like trying to see fog in a pitch-black forest. It doesn't emit much light, and what little it does gets drowned out by the brilliant glare of nearby stars and galaxies. So how do you find something that's practically invisible? Scientists have turned to clever tricks, like hunting for faint distortions in the light of distant quasars, celestial beacons so bright they can illuminate the gas clouds in front of them. When WIM absorbs specific wavelengths of that light, it leaves behind a cosmic fingerprint. And recently, the X-ray eyes of telescopes like Chandra and XMM Newton have begun picking up whispers of this elusive material. But the numbers still don't add up. Even accounting for WIM, half the universe's ordinary matter remains unaccounted for. Could the answer lie in something even more elusive? Some speculate that the missing baryons might be hiding in even sparser regions, forming vast cold reservoirs that current instruments simply can't detect. Others wonder if our understanding of physics itself needs an overhaul, that maybe, just maybe, we've been looking at the cosmic ledger all wrong. One thing's certain: solving this mystery won't just fill a gap in our maps of the universe. It could rewrite the rules of how matter behaves on the grandest scales imaginable. And here's the kicker: if WIM or some other hidden structure really does hold the key, it means the cosmic web isn't just a backdrop to the universe's drama. It's the main stage, silently orchestrating the fate of galaxies while keeping its secrets locked tight. Until we crack this case, the missing baryons will remain one of the universe's most tantalizing disappearing acts. If ordinary matter is playing hide and seek in the cosmic web, dark matter is the ghost holding the entire structure together, utterly invisible yet impossible to ignore. While we can't see it, touch it, or even directly measure it, this mysterious substance makes up roughly 25% of the universe's total mass, weaving itself into the filaments with gravitational threads stronger than steel. Without dark matter, the cosmic web wouldn't exist as we know it. Galaxies would never have clumped together, and those shimmering filaments stretching across the cosmos would have unraveled eons ago. So how do we study something that refuses to interact with light or matter? The answer lies in the shadows it casts. Supercomputer simulations reveal dark matter's fingerprints everywhere. Dense halos around galaxies, vast bridges between clusters, and intricate knots where filaments intersect. These digital universes show dark matter as the cosmic architect, sculpting the web's skeleton long before ordinary matter caught up, but simulations alone aren't proof. Enter gravitational lensing, one of astronomy's most brilliant detective tricks. When light from distant galaxies passes near a filament, dark matter's gravity bends that light like a funhouse mirror, distorting the shapes of galaxies behind it. By measuring these distortions, scientists can literally map the invisible, tracing dark matter's tendrils across the sky. Yet for all its gravitational muscle, dark matter remains frustratingly elusive at the particle level. Laboratories buried deep underground hunt for hypothetical particles like WIMP, weakly interacting massive particles, that might finally explain this cosmic phantom. So far, every detector has come up empty, leaving researchers to wonder, is dark matter even a particle at all? Some theories suggest it could be primordial black holes, remnants of the universe's fiery birth. Others propose exotic quantum fields stretching across space. The wildest ideas hint that dark matter might not be matter at all, but a glitch in our understanding of gravity itself. What makes this hunt so urgent? Because dark matter doesn't just shape the cosmic web, it holds the key to our cosmic fate. The amount and behavior of dark matter determine whether the universe will keep expanding, collapse in on itself, or tear apart. Every filament, every galaxy, every atom in your body exists because dark matter's gravitational whisper guided them into being. And until we unravel its true nature, the grandest structure in existence will remain half in shadow, its architect hiding in plain sight. Magnetic fields weave through the cosmos like invisible rivers of force, and nowhere are they more mysterious than in the vast filaments of the cosmic web. These aren't just faint whispers of magnetism, they're colossal structures stretching millions of light years, with strength rivaling those found near pulsars or black holes. But here's the puzzle: magnetism on this scale shouldn't exist. According to classical physics, the universe's primordial magnetic fields should have diluted to near nothingness over billions of years of expansion. Yet somehow, these filaments are crackling with magnetic energy, as if the cosmos itself forgot to follow its own rules. So where do these fields come from? One theory points to the turbulent infancy of the universe. In the chaotic aftermath of the Big Bang, violent plasma currents might have twisted space-time like a dynamo, seeding faint magnetic fields that later amplified as galaxies and filaments formed. Another idea suggests that supermassive black holes, firing jets of charged particles across intergalactic space, could have painted magnetism onto the cosmic web like cosmic graffiti artists. But neither explanation fully accounts for the sheer scale and uniformity of these fields. Some filaments, like the one connecting the Abell 39 and 40 galaxy clusters, show magnetic alignment over distances so vast it defies conventional astrophysics. What's even stranger is what these fields do. They're cosmic accelerators hurling particles to near-light speeds. When high-energy cosmic rays, those enigmatic particles bombarding Earth from deep space, zip through filamentary magnetic fields, they gain tremendous energy like surfers catching an endless wave. This might explain why we detect cosmic rays with energies so high they shouldn't exist under known physics. Even more intriguing, these fields could shape galaxies themselves. Simulations show that magnetic forces in filaments might guide gas flows during galaxy formation, determining whether a galaxy becomes a spiral like the Milky Way or a featureless elliptical blob. Yet for all their influence, these magnetic fields remain nearly invisible. Detecting them requires observing the faint polarization of light from distant quasars or mapping the synchrotron glow of electrons spiraling along magnetic lines. Each new observation deepens the mystery. Some filaments exhibit bizarre, knotted magnetic structures, while others show eerie uniformity, as if an unseen hand combed them into perfect alignment. The implications are staggering. If magnetic fields permeating the cosmic web are this powerful, they could rewrite our understanding of how structure forms in the universe. They might even hold clues to the nature of dark energy or the fate of cosmic expansion. One thing's clear: these hidden forces are anything but passive. They're active players in the universe's grand story, bending particles to their will and quietly shaping everything we see. And until we unravel their secrets, we're only seeing half the picture of the cosmic web. Buried within the afterglow of the Big Bang lies an anomaly so bizarre it challenges our understanding of the cosmos itself: the Great Cold Spot. This cosmic bruise, stretching over 1.8 billion light-years across the southern sky, appears in the cosmic microwave background as a chilling void, roughly 70 microkelvin colder than its surroundings. At first glance, it might seem like a statistical fluke, a random dip in temperature, but the odds of such a profound cold spot appearing naturally, less than 2%. So what carved this frozen scar into the fabric of the universe? One leading theory points to a supervoid, an enormous, nearly empty region of space where the cosmic web's filaments stretch thin, leaving vast deserts between galaxies. Supervoids aren't just empty space, they're gravitational potholes. When light passes through them, it loses energy climbing out, a phenomenon called the integrated Sachs-Wolfe effect. The result: a cold imprint on the CMB, like a shadow cast by absence itself. The Great Cold Spot aligns eerily with one such void, known as the Eridanus supervoid, a cavern so vast it could swallow thousands of Milky Ways. But here's where things get strange. Even the largest supervoids we've mapped shouldn't produce a temperature drop this extreme. Simulations suggest the Eridanus void is at least 10 times too small to explain the cold spot's depth. This discrepancy has led some cosmologists to propose wilder explanations. Could it be evidence of a collision with a parallel universe, a cosmic bruise from a long-ago encounter with another bubble of spacetime? Others suggest exotic physics, like dark energy interacting with matter in ways we haven't yet imagined. Then there's the plot twist: not everyone agrees the cold spot is real. Skeptics argue it might be an artifact of foreground interference, dust in our own galaxy casting a deceptive chill. Or perhaps it's a statistical mirage, a trick of the mind when staring at the universe's noise. Yet every time new data comes in, from Planck satellite measurements to detailed galaxy surveys, the cold spot stubbornly remains, colder and more puzzling than ever. What makes this cosmic riddle so thrilling is what it reveals about our place in the universe. If the Great Cold Spot is truly a supervoid's fingerprint, it's a reminder of how deeply the cosmic web structure imprints itself on everything we see. But if it's something stranger, it could be the first crack in our cosmological models, a glimpse of physics beyond Einstein's wildest dreams. One thing's certain: until we solve this frozen mystery, the Great Cold Spot will loom over cosmology like a question written in the sky. Nestled along the faint tendrils of the cosmic web, ultra-diffuse galaxies are the universe's quiet rebels, ghostly, sprawling islands of stars so thin you could peer straight through them. These enigmatic objects, some as wide as the Milky Way but with 1,000 times fewer stars, shouldn't exist according to conventional galaxy formation models. Yet there they are, clinging like cosmic cobwebs to the filaments, their very presence raising questions that could upend our understanding of dark matter and stellar evolution. Take Dragonfly 44, one of the most famous ultra-diffuse galaxies. It glows with only 1% of the Milky Way starlight, yet moves with the gravitational heft of a galaxy crammed with dark matter. This mismatch is staggering. Normally, a galaxy this dim would be ripped apart by its neighbor's gravity, but something invisible, something massive holds it together. The twist: when astronomers measured Dragonfly 44's dark matter halo, they found it nearly as hefty as our own galaxies, despite having almost no stars to show for it. It's like finding a featherweight boxer who hits with the force of a heavyweight champion. Even stranger is where these galaxies choose to live. Most lurk near the dense intersections of cosmic filaments, where dark matter flows like rivers into a delta. Simulations suggest these regions should be birthplaces of bustling, star-packed galaxies, not these faint wraiths. One theory proposes that ultra-diffuse galaxies are failed galaxies, objects whose gas was stripped away by violent encounters early in cosmic history, leaving them starved but stubbornly intact. Others speculate they're relics of a chaotic era when dark matter clumped differently, creating pockets where stars spread out instead of bunching together. Then there's the star formation puzzle. Some ultra-diffuse galaxies, like NGC 1052DF2, appear to have hardly ever formed stars at all. Their skies are eerily empty, as if someone pressed pause on stellar birth billions of years ago. Yet others, like the oddly named Matless J, dark matter is real, and its cold, show faint blue tendrils of newborn stars, proof that even in these ghostly realms, star formation flickers on. What makes these galaxies so crucial isn't just their strangeness. They're cosmic stress tests for dark matter theory. If our models can't explain why dark matter piles up in some galaxies while stars don't, we might be missing a fundamental piece of the puzzle. Some researchers even suggest ultra-diffuse galaxies could be the key to spotting exotic dark matter particles, whose faint interactions might leave traces in these ultra-low-density environments. Every new discovery deepens the mystery. Recent observations reveal ultra-diffuse galaxies with no dark matter at all, a contradiction that shouldn't exist if dark matter is as universal as we think. Whether they're cosmic accidents, dark matter anomalies, or something even weirder, one thing's clear: these faint ghosts of the cosmic web are forcing us to rethink the rules of galaxy formation. And with each one we find, the universe whispers another question we can't yet answer. The cosmic web's filaments should be bustling with galaxies, each one a glittering node in this vast interconnected network. Simulations predict thousands of dwarf galaxies swarming around these threads, like fireflies caught in invisible spider silk. Yet when astronomers point their telescopes at these regions, they find eerie silence. Where are all the missing galaxies? This glaring mismatch between prediction and reality, known as the missing satellites problem, has haunted cosmologists for decades, forcing us to question whether our theories of galaxy formation are fundamentally flawed or if we're simply not seeing the full picture. Take the local group, our galactic neighborhood. Dark matter simulations suggest there should be hundreds of small satellite galaxies orbiting the Milky Way and Andromeda. Instead, we've spotted barely a few dozen. Some of this discrepancy might come from observational bias. Dwarf galaxies are faint, often drowned out by the glare of their massive neighbors or obscured behind curtains of interstellar dust. Modern telescopes like the Vera Rubin Observatory are now scouring these filaments with unprecedented sensitivity, hunting for these elusive cosmic minnows. But even as they uncover more ultra-faint dwarfs, the numbers still fall short. The deeper mystery lies in why these galaxies didn't form as expected. One leading theory blames the very nature of dark matter. If dark matter is cold, as most models assume, it should clump readily, creating dense pockets where gas collapses into stars. But what if dark matter interacts with itself or with other particles in ways that suppress these clumps? Some simulations now explore warm, dark matter scenarios where lighter particles move too fast to form the tiny structures needed for dwarf galaxies. Others suggest cosmic reionization. The universe's early blast of ultraviolet light might have sterilized gas in the smallest halos, preventing stars from ever igniting. Then there's the destruction hypothesis. Filaments are violent places where tidal forces and galaxy collisions can shred smaller objects apart. Perhaps many dwarfs formed but were later torn to pieces, leaving behind only streams of stars as tombstones. The Gaia spacecraft has spotted these ghostly trails around the Milky Way, implying a history of cosmic cannibalism. But even accounting for this, the gap persists. The implications ripple far beyond our local universe. If filaments truly host fewer galaxies than predicted, it could mean the cosmic web is far less efficient at building structures than we thought, or that our understanding of dark matter's role is incomplete. Some researchers even speculate that certain filaments might be dark, composed almost entirely of shadowy matter with no stars at all. Each unanswered question tightens the knot. Are we missing galaxies, or is the universe hiding them from us? Until we solve this puzzle, the cosmic web's silent threads will keep whispering secrets we're only beginning to hear. Filaments are supposed to be the universe's quiet highways, long, winding rivers of gas and dark matter where galaxies hitch a ride toward denser clusters. But astronomers have stumbled onto something that upends this serene picture. Some of these cosmic threads are spinning, not just drifting, not merely flowing, but rotating on colossal scales, as if the universe itself twisted them into motion. This discovery throws a wrench into everything we thought we knew about how structure forms in the cosmos, because filaments shouldn't have angular momentum. Think of it like stirring a cup of coffee. The swirl comes from the spoon's force, but in the early universe there was no cosmic spoon to set these filaments spinning. Gravity alone can't explain it. Filaments form where matter collapses along straight lines, not in spinning vortices. Yet observations of galaxy clusters like Abell 1656 reveal galaxies on opposite sides of a filament moving in opposite directions like cars on a rotating Ferris wheel. The filament itself is the axle, rotating at speeds that would fling stars off a galactic disk. How does something hundreds of millions of light years long start spinning without breaking the laws of physics? One radical idea points to the universe's turbulent infancy. In the first fractions of a second after the Big Bang, quantum fluctuations might have imprinted tiny twists on spacetime itself. As the cosmos expanded, these twists amplified, stretching into the large-scale rotation we see today. Others suggest cosmic collisions are to blame when galaxy clusters slam into each other. Their titanic mergers could torque the filaments between them like a twisted rope. But neither explanation fully accounts for the sheer scale of the motion. We're talking about structures so vast their rotation would take billions of years to complete a single turn. Then there's the dark matter factor. If dark matter particles interact even faintly, scattering off each other like billiard balls, those microscopic collisions could transfer momentum across entire filaments. Some theorists even speculate that primordial magnetic fields threading through the early universe might have acted like cosmic strings, dragging gas into rotation as they tightened. But the wildest implication, filament rotation could rewrite the story of galaxy formation. Spin is the hidden ingredient that determines whether gas clouds collapse into disks like the Milky Way or chaotic ellipticals. If filaments are spinning, they might pass that angular momentum down to galaxies like an inheritance, shaping their destinies before they even formed. It's a cosmic cascade from the twist of the web to the whirl of a spiral arm. Every new observation deepens the mystery. Some filaments rotate clockwise, others counterclockwise. A few show no spin at all, as if the universe capriciously chose which threads to set in motion. Until we understand why, these whirling giants remind us that even the grandest structures in existence still hold secrets written in the slow, silent turn of the cosmic web. When light from a distant quasar pierces through the cosmic web, it doesn't arrive untouched, it carries scars. Astronomers call these scars the Lyman alpha forest, a bizarre pattern of absorption lines etched into the quasar's spectrum like tally marks on a prison wall. Each line represents hydrogen gas lurking in the filaments, snatching away specific wavelengths of light as it passes through. But here's what makes this forest so unsettling. Its trees aren't growing where they should. The distribution of these lines defies our most sophisticated simulations, revealing a cosmic web far messier and more enigmatic than we ever predicted. Picture a quasar's light as a beam passing through a labyrinth of foggy corridors, the filaments of the cosmic web. Every time that light encounters a cloud of neutral hydrogen, it gets absorbed at a characteristic wavelength, leaving a dark line in the spectrum. The closer the gas is to us, the more redshifted the line appears, creating a forest of absorption features stretching across the spectrum. In theory, these lines should trace the web's structure perfectly, matching the delicate network seen in supercomputer models. Instead, they paint a portrait of chaos. Some regions expected to be dense with gas show startling gaps, while others, predicted to be near empty, teem with absorption lines as if the universe spilled its hydrogen where it wasn't supposed to. The discrepancies run deep. Simulations suggest gas in filaments should be smoothly distributed, shaped by gravity's gentle pull. Yet the Lyman alpha forest reveals clumps and voids on scales too small for current models to explain, like finding sudden clearings in a jungle that no map warned you about. Even more puzzling, some quasars show fewer absorption lines than they should, as if their light passed through ghostly tunnels where gas mysteriously vanished. One leading explanation points to the fierce ultraviolet radiation from early galaxies, which might have ionized patches of hydrogen, leaving behind a patchwork of illuminated and shadowed regions. But when astronomers tweak their simulations to include this effect, the math still doesn't add up. Then there's the temperature problem. Filament gas should cool predictably as the universe expands, yet the Lyman alpha lines hint at pockets of gas too hot or too cold for their environments. Some researchers speculate that turbulence from ancient cosmic shocks, leftover ripples from the universe's violent youth, could be stirring the gas unpredictably. Others wonder if dark matter's quirks are to blame, its invisible claws kneading the gas into shapes we don't yet understand. But the real shocker, the forest might be hiding more than just hydrogen. Occasionally, absorption lines appear at wavelengths matching heavy elements like carbon and oxygen elements that shouldn't exist far from galaxies. Their presence suggests filaments aren't the pristine highways we imagined, but littered with debris from ancient supernova or galactic winds, as if the cosmic web secretly hoarded stardust in its folds. Every new quasar observed adds another layer to the mystery. Some show forests so dense they're nearly impenetrable, while others appear oddly sparse, as if the filaments along their sightline forgot to form properly. What's clear is this: the Lyman alpha forest isn't just a curiosity. It's a cipher encoding the true structure of the cosmic web in light and shadow. And until we crack its code, we're left with a universe that refuses to follow its own blueprints. The cosmic web is meant to follow rules, delicate filaments tracing the faint blueprints of dark matter, knitting the universe together in a predictable tapestry. But some filaments laugh in the face of those rules. They stretch farther than physics says they should, flaunting sizes so absurd they make cosmologists double-check their calculators. Leading the charge, the Hercules Corona Borealis Great Wall, a filament so colossal it could swallow 10,000 Milky Ways side by side and still have room for seconds. At 10 billion light-years across, this isn't just a structure, it's a cosmic empire, and its very existence threatens to crack one of astronomy's foundational principles, the cosmological principle. This principle states that on large scales, the universe should look roughly the same no matter where you're standing, no preferred directions, no privileged locations. It's why we expect filaments to top out around 1 billion light-years. But Hercules' corona borealis blows past that limit like a sprinter ignoring the finish line. Spotting it was like finding a mountain range taller than Earth's diameter. It simply shouldn't be possible. Even stranger, it's not alone. The Sloan Great Wall, the Boss Great Wall. These titanic threads keep turning up in galaxy surveys, each one stretching the definition of filament to its breaking point. So how did these giants slip past the universe's zoning laws? One theory suggests they're not single filaments but superstructures, multiple filaments braided together by gravity like cosmic rope. But even that explanation strains credibility. Simulations show dark matter's gentle tug couldn't weave something this vast without help. Some researchers point to early universe quirks, regions where matter clumped more aggressively, perhaps due to exotic energy fields we haven't yet discovered. Others whisper about primordial quantum fluctuations gone wild, seeds planted in the Big Bang's first moments that grew into these behemoths. Then there's the measurement problem. Mapping something 10 billion light-years long from our tiny vantage point is like trying to measure a skyscraper with a ruler held at arm's length. Could Hercules' corona borealis be a trick of perspective, smaller structures lined up deceptively? Detailed 3D reconstructions say no. The galaxies within it move in concert, bound by gravity, proving it's a single, coherent monster. What keeps astronomers up at night isn't just the size, it's the timing. These walls are ancient, dating back to when the universe was a fraction of its current age. For them to grow this large so quickly defies the standard model of cosmic growth, like a toddler bench pressing a truck. If our models can't explain their existence, what else might we be missing? The answer could rewrite cosmology, proving the universe isn't as uniform as we thought, or that dark energy, dark matter, or something even stranger played tricks on gravity itself. Until then, these two big filaments loom over astronomy like unanswerable riddles. They're reminders that for all our maps and models, the cosmic web still holds regions where the rules don't apply, and where the universe, it seems, enjoys showing off. Filaments should be dark, long, shadowy tendrils where matter whispers rather than shouts. Yet when astronomers train ultraviolet and X-ray telescopes on these cosmic threads, they catch something impossible, a faint, ghostly glow. Not just scattered light from nearby galaxies, but emissions woven into the filaments themselves, as if the universe left its lights on in these vast, empty corridors. This isn't just stray energy, it's a signal without a clear source, a cosmic hum that shouldn't be there. And the closer scientists look, the stranger it gets. Take the X-ray glow detected in filaments linking galaxy clusters like Abell 2228. The gas here is scorching millions of degrees, but traditional physics says it should cool rapidly, fading into darkness. Instead, it flickers with X-rays far brighter than expected, like a dying ember suddenly flaring back to life. One explanation, shock waves rippling through the filaments, generated as galaxies and clusters jostle for position in the cosmic web. These collisions could heat the gas to X-ray temperatures, but the math rarely adds up. Some filaments glow too uniformly, too persistently, as if powered by something more exotic than mere turbulence. Then there's the ultraviolet puzzle. Satellites like Hubble have spotted diffuse UV light clinging to filaments, a phenomenon dubbed the Cosmic Webs Lyman alpha blobs on steroids. Unlike the pinpoint glow of stars, this emission spreads across millions of light-years, untethered to any visible source. One theory suggests it's the echo of ancient quasars, their radiation lingering like a fading shout in an empty hall. Others propose it's the work of decaying dark matter, with hypothetical particles like sterile neutrinos annihilating and releasing UV photons as they vanish. But the wildest possibility, these filaments might be cosmic power lines channeling energy from realms we can't yet see. Magnetic fields threaded through the web could accelerate particles to extreme energies, generating X-rays far from any galaxy. Or perhaps the glow hints at undiscovered quantum processes, dark matter interacting with itself in ways that leave behind traces of light. What makes this mystery so tantalizing is its scale. These emissions aren't local quirks, they're woven into the fabric of the universe, a faint but pervasive signature that something fundamental is missing from our models. Every new observation deepens the intrigue. Some filaments glow unevenly, flickering like faulty neon signs. Others pulse rhythmically, as if responding to a hidden cosmic heartbeat. Until we unravel this enigma, the cosmic web's ghostly light serves as a reminder. Even in the darkest reaches of space, the universe refuses to stay silent. And whatever's causing that glow, whether shock waves, dark matter, or something beyond our current physics, it's rewriting the rules of how energy moves through the cosmos, one filament at a time. Galaxies aren't just drifting aimlessly through the cosmic web, they're racing toward something. Or at least that's what a team of scientists claimed in 2008 when they spotted an eerie pattern in the motion of hundreds of galaxy clusters. These colossal structures, each containing thousands of galaxies, weren't moving randomly. They were all streaming in the same direction at breakneck speeds, as if pulled by an invisible hand. This bizarre motion, dubbed the dark flow, pointed toward a single patch of sky just beyond the edge of the observable universe. The implications were staggering. Something massive, perhaps a structure so enormous it defies comprehension, was tugging on our cosmic neighborhood from beyond the veil of reality itself. At first, the discovery seemed impossible. The universe's expansion should dilute any gravitational pull over vast distances, leaving galaxies to drift apart like leaves on a receding tide. Yet here was evidence of coordinated motion on scales exceeding 3 billion light-years, far beyond where any known cosmic force should reach. The team, led by astronomer Alexander Kashlinsky, traced the motion using the cosmic microwave background, the afterglow of the Big Bang. As galaxy clusters plow through space, their hot gas scatters CMB photons, leaving faint imprints called the kinematic Sunyaev-Zeldovich effect. By mapping these distortions across 700 clusters, they found a consistent drift toward the constellations Centaurus and Vela, as if the entire observable universe were tipping toward some unseen mass. Skeptics pounced immediately. Could this be a measurement error, a quirk of the data? Independent teams scrambled to replicate the findings with mixed results. Some analyses confirmed the dark flow's existence, while others found no evidence at all. The controversy deepened when later studies suggested the signal might arise from incomplete CMB maps or foreground interference. But Kashlinsky's team dug in, refining their methods and expanding their dataset. By 2010, they claimed the dark flow extended even farther, out to a mind-bending 5 billion light-years. If real, this wasn't just a local anomaly, it was a cosmic current sweeping through the web itself. What could possibly exert such a pull? One radical theory points to an ancient scar from the Big Bang. In the theory of eternal inflation, our universe might be one bubble among countless others in a vast multiverse. If a neighboring bubble collided with ours long ago, the gravitational wake of that collision could still be dragging matter toward it, like a moon's tidal pull lingering after the tide has gone out. Others speculate about a supermassive structure lurking just beyond our observational horizon, a great attractor on steroids, so colossal it bends the rules of cosmology. But here's where filaments enter the picture. If the dark flow exists, the cosmic web's tendrils might be its conduits, funneling galaxies along invisible highways toward this mysterious destination. Some simulations suggest dark matter's gravitational scaffolding could amplify tiny initial tugs into coherent flows across vast distances. Or perhaps filaments themselves are moving, their immense mass responding to forces we can't yet see. The stakes couldn't be higher. If the dark flow is real, it implies our universe isn't as uniform as we thought. That beyond the edge of what we can observe, something lurks that challenges the cosmological principle itself. If it's an illusion, it reveals just how easily our measurements can deceive us. Either way, this controversy forces us to confront a humbling truth. We might be floating on a cosmic river whose source remains hidden in the dark. Galaxies don't float alone in the cosmic void. They're supposed to be anchored by thick, dark matter tendrils, fed by the cosmic web's invisible rivers of gas and gravity. But something's wrong with that picture. When astronomers mapped the surroundings of certain galaxies, they found halos floating in isolation, like islands severed from their continental roots. No filaments, no connections, just empty space where the cosmic web's threads should be. This glaring absence, known as the filament halo disconnect, isn't just a minor oversight in our models. It's a direct challenge to how we think the universe builds its largest structures. Take the galaxy NGC 4921, a massive spiral floating in a void of unsettling emptiness. According to simulations, its halo should be fed by at least 3 major filaments, each pumping gas and dark matter into its core like cosmic Roman IV drips. Yet deep observations reveal nothing, no streams of hydrogen, no telltale trails of infalling dwarf galaxies. It's as if this galaxy formed in defiance of the rules, thriving without the web's nourishment. NGC 4921 isn't alone. Surveys like the Sloan Digital Sky Survey have catalogued dozens of similar orphan halos, each one a puzzle wrapped in enigma. The implications are profound. If filaments really are the universe's delivery system for galaxy growth, how did these halos get so massive without them? One possibility is timing. Maybe the filaments evaporated. In the early universe, violent quasars or supernova winds could have ionized the surrounding gas, stripping filaments bare before they fully formed. Another theory points to dark matter's quirks. If certain types of dark matter interact more weakly than we thought, they might not clump into filaments as efficiently, leaving halos stranded. But there's a wilder idea. What if these halos didn't form from filaments at all? Some cosmologists speculate they could be remnants of a rare, top-down collapse, an era when entire clouds of gas fragmented directly into galaxies without first threading into filaments. Or perhaps they're cosmic hitchhikers, galaxies that drifted away from their parent filaments over billions of years, leaving no trace of their origins. The real shocker came when researchers noticed a pattern. Isolated halos tend to cluster in specific regions of the sky, as if the cosmic web itself has bald patches where the threads refuse to grow. This selective absence hints at something deeper, a fundamental unevenness in how dark matter and gas were distributed after the Big Bang. Maybe quantum fluctuations left some regions of the early universe too smooth to spawn filaments, creating voids within voids where galaxies formed against all odds. The mystery doesn't end there. Some disconnected halos show bizarre star formation rates, either burning too fast or barely flickering, as if their isolation altered their very life cycles. Others host supermassive black holes that seem improbably large for their galactic homes, suggesting their growth followed a different set of rules. Every observation adds another layer to the puzzle, forcing us to question whether filaments are as universal as we once believed. Until we crack this case, the filament halo disconnect stands as a stark reminder. The cosmic web isn't just a passive scaffold. It's a dynamic, unpredictable force, one that can build galaxies with one hand and abandon them with the other, leaving behind cosmic orphans with stories we're only beginning to decipher. Hidden in the faint glow between galaxies lies a whisper from the universe's youth, ancient light, trapped in the cosmic web's filaments like fossils preserved in amber. This isn't starlight or the afterglow of the Big Bang, but something far more elusive, the residual radiation from collisions and decays that shaped the web's violent adolescence. Imagine two filaments, each a river of dark matter and gas, crashing together in slow motion over millions of years. The shock waves from these cosmic pile-ups heat gas to blistering temperatures, leaving behind a spectral fingerprint, a ghostly afterglow that lingers long after the chaos has faded. The hunt for this fossil light has led astronomers to some of the most sensitive telescopes ever built. Instruments like the Atacama Large Millimeter Array scan the skies for subtle distortions in the cosmic microwave background, hunting for the telltale imprints of filament collisions. One breakthrough came in 2019 when researchers spotted a faint but unmistakable signal in the data from the Planck satellite. Stretching between the clusters Able 3391 and Able 3395, the glow matched predictions for gas heated to millions of degrees during a filament merger. The kicker, the energy didn't come from stars or black holes, but from the sheer violence of the web's own growth. But the real treasure lies in what this light reveals about the universe's turbulent past. Filament collisions aren't just cosmic fender benders, they're particle accelerators on a scale that dwarfs anything on Earth. When gas slams together at thousands of kilometers per second, it generates shock waves powerful enough to rip electrons from atoms, creating a plasma that glows in X-rays and radio waves. In some cases, these collisions might even produce elusive high-energy neutrinos, the very same particles that ice-bound detectors like ice cube catch streaming from deep space. Then there's the decay hypothesis. Some theorists argue this fossil light could be the death rattle of dark matter itself. If certain hypothetical particles like sterile neutrinos or actions exist, they might decay into photons over billions of years, leaving behind a diffuse glow woven through the filaments. The challenge, distinguishing this signal from the cacophony of other cosmic emissions. It's like trying to hear a single violin in a symphony orchestra playing at full volume. What makes these faint echoes so powerful is their longevity. Unlike the brief blaze of a supernova, filament glow lingers for epochs, preserving a record of the web's growth across cosmic time. By mapping its distribution, astronomers can trace how filaments evolved, how they funneled gas into galaxies, and even how dark energy might be stretching them apart today. Yet every answer uncovers new questions. Why do some filaments glow brighter than others? Are we seeing the aftermath of rare, catastrophic mergers or the steady hum of countless smaller collisions? And could this fossil light hold clues to the universe's most elusive secret, the true nature of dark energy itself? Until we piece together this cosmic palimpsest, the web's ancient light will keep whispering secrets from a time when the universe was still learning how to weave its grandest tapestry. The cosmic microwave background, the CMB, is often called the universe's baby picture, a snapshot of the first light to travel freely through space. Its patterns, imprinted when the cosmos was just 380,000 years old, reveal the seeds of all future structure, tiny fluctuations in density that would one day grow into galaxies, clusters, and the cosmic web itself. But here's where things get strange. Those ancient ripples aren't just random. Some of them align with the very filaments we see today, as if the universe's first whispers somehow dictated where its largest structures would form billions of years later. This eerie alignment, first spotted in 2014, defies expectations. The CMB's polarization, the direction its light waves vibrate, should have no memory of where filaments would eventually emerge. Yet studies of massive surveys like Planck and Boss reveal filaments preferentially oriented along the same axis as the CMB's large-scale polarization. It's like finding a newborn's fingerprints perfectly matching the blueprint of the city they'd build as an adult, an impossible coincidence begging for explanation. One theory digs deep into the universe's infancy. In its first trillionth of a second, spacetime may have undergone a violent expansion called inflation. stretching quantum fluctuations into cosmic-scale ripples. If inflation wasn't perfectly uniform, if it had a preferred direction, like a stretchy fabric tugged harder one way than another, it could have imprinted that directionality onto both the CMB and the Webb's future skeleton. Some simulations even suggest exotic fields, remnants of inflation, might have subtly guided dark matter into these aligned filaments. Then there's the dark flow connection. The same mysterious force potentially dragging galaxy clusters toward the unseen could have also nudged primordial plasma, leaving behind polarized light and filament alignments as collateral damage. Skeptics counter that the alignment might be a trick of perspective filaments appearing to line up due to our limited vantage point in the universe. Yet the signal persists even when accounting for observational biases, hinting at something deeper. The implications are staggering. If filaments truly remember the CMB's polarization, it means the universe's largest structures were choreographed at birth, their growth dictated by forces we've only begun to fathom. It's a cosmic conspiracy spanning 13.8 billion years, one that challenges us to rethink not just how the web formed, but whether the universe itself has hidden symmetries we're only now glimpsing. Filaments should be brimming with gas, vast reservoirs of hydrogen and helium left over from the Big Bang, fueling galaxy growth for billions of years. Yet when astronomers point their instruments at certain cosmic threads, they find something baffling: ghostly corridors where the gas has all but vanished. These empty filaments defy every simulation, leaving scientists scrambling to explain where the missing material went. One of the most striking examples lies between the galaxy clusters Abell 1367 and Abell 1369. This filament, stretching over 50 million light-years, contains less than half the gas predicted by models, as if someone siphoned it away in the night. So where did it go? The prime suspect: active galactic nuclei, supermassive black holes lurking at the hearts of galaxies, capable of cosmic-scale destruction. When these monsters feed, they unleash torrents of energy, blasting jets of plasma at nearly light speed. These jets can punch through entire galaxy clusters, but their real power shines in filaments. Like cosmic pressure washers, they might strip gas from the delicate threads, flinging it into the void beyond. Evidence for this comes from the Perseus cluster, where the black hole's jets have carved vast bubbles in the surrounding gas, leaving behind eerie, empty cavities. If similar eruptions occurred in filaments, they could explain the vanishing act, but there's a twist. Not all gas-poor filaments sit near active galaxies, suggesting other culprits are at work. Another theory points to an invisible thief: rapid cooling. Filament gas should linger for billions of years, slowly condensing into galaxies. But if certain conditions like unexpected metal contamination or turbulence made it cool too fast, it could have collapsed directly into stars, draining the filament before astronomers got a chance to see it. The Spiderweb galaxy, a chaotic nest of merging protogalaxies, offers a clue. Here, gas cools so rapidly it forms stars at a rate hundreds of times faster than the Milky Way. If this frenzy happened inside filaments, it could leave them starved and skeletal. Then there's the dark horse explanation: the gas isn't missing at all, it's just hiding. Some simulations suggest filaments might contain ultra-dense, cold clumps of gas so faint they evade detection. These dark clouds could be the universe's stealthy reservoirs, camouflaged against the cosmic background until better telescopes uncover them. The ALMA telescope recently spotted hints of this in the filament near the galaxy NGC 1277, a wispy trail of cold molecular gas that standard surveys had overlooked. But the wildest idea: the gas might have been stolen by another universe. In brain cosmology, our universe could be a membrane floating in higher dimensional space, occasionally brushing against others. If a collision occurred along a filament, it might have siphoned matter away, leaving behind cosmic breadcrumbs we've yet to decode. While speculative, it underscores a humbling truth: the cosmic web's gaps aren't just empty spaces. They're puzzles waiting to rewrite physics. Some filaments in the cosmic web are cosmic roadways, broad and thick enough to funnel entire galaxies along their length. But others defy logic, threads so impossibly thin they shouldn't exist. These are the too thin filaments, wispy tendrils of gas and dark matter stretching hundreds of millions of light years while remaining narrower than some star clusters. According to our best simulations, gravitational collapse and gas dynamics should have fattened them up long ago. Yet there they are, delicate as spider silk, challenging everything we know about how structure forms in the universe. Take the thread connecting the galaxy clusters MAX J0717 and MAX J0718. This filament, observed in stunning detail by the Hubble Space Telescope, spans 60 million light-years but measures less than 2 million light-years wide, thinner than the distance between the Milky Way and Andromeda. At that scale, it's like finding a single human hair stretched from New York to Los Angeles. Conventional models say gravity should have thickened it tenfold by now, pulling in surrounding matter like a cosmic vacuum cleaner. Instead, it's remained oddly anorexic, as if some invisible force stunted its growth. What keeps these filaments so lean? One theory points to dark energy's relentless push. As the universe expands, dark energy might be stretching filaments taut, counteracting gravity's natural tendency to bulk them up. Another idea suggests turbulence in the early universe. Violent shocks from supernova or quasar jets could have sliced filaments into these bizarrely narrow strands, like a cosmic cheese wire cutting through primordial gas. Then there's the dark matter factor. If dark matter particles interact more weakly than we think, barely glancing off one another, they might not clump efficiently, leaving filaments starved of their gravitational scaffolding. Some simulations even hint that magnetic fields could play a role, their invisible lines of force acting like cosmic corsets, squeezing filaments into unnatural thinness. But the most puzzling cases are filaments that aren't just thin, they're lumpy. The thread linking the clusters Able 222 and Able 223, for instance, isn't a smooth river of gas. It's a string of beads with dense knots of matter spaced like pearls on a necklace. This violates every expectation of how gas should behave over cosmic time. Left alone, pressure differences should have smoothed it into uniformity. Instead, it clings to its patchy structure, as if some unseen hand molded it that way on purpose. The implications ripple far beyond cosmic curiosities. If filaments can stay thin and lumpy against all odds, our simulations of galaxy formation might be missing a critical piece of physics. Galaxies fed by these wispy threads would grow differently, starved of gas or bombarded by intermittent surges of material. Some researchers speculate these anomalies could even hint at exotic dark matter behavior or undiscovered forces that only manifest on the largest scales. Every new observation adds another wrinkle. Some thin filaments flicker with unexpected X-ray emissions, as if hiding violent processes beneath their fragile surfaces. Others show bizarre alignments with the cosmic microwave background, suggesting their structure was imprinted at the dawn of time. Until we solve this riddle, these cosmic threads remain a silent protest against our models, reminding us that the universe's grand design still holds twists we've yet to unravel. Fast radio bursts, those mysterious milliseconds-long blasts of cosmic energy, have puzzled astronomers since their discovery, but what's even stranger is where some of them come from. A handful of these ultra-powerful signals trace back to the very intersections of cosmic filaments, as if the web itself is firing off cryptic messages. This isn't just a coincidence. These regions, where multiple filaments collide like highways merging into a cosmic freeway, are churning with conditions unlike anywhere else in the universe. Superheated plasma, tangled magnetic fields, and gravitational chaos create an environment ripe for the kind of extreme physics that could spawn FRBs. So why do these fleeting signals seem to favor the web's busiest crossroads? One clue lies in the plasma itself. filament intersections are pressure cookers of ionized gas where particles are accelerated to near light speeds. When dark matter's gravity pulls filaments together, the resulting shock waves can turbocharge this plasma, creating conditions similar to those near neutron stars' known FRB factories. But here's the twist: some of these intersection FRBs repeat, flickering on and off like a malfunctioning beacon. That's rare in the FRB world, and it suggests something more sustained than a one-off collision. Could these regions harbor hidden compact objects, rogue neutron stars, or even primordial black holes trapped in the Webb's gravitational knots? Then there's the magnetic mayhem. Filaments are threaded with powerful, large-scale magnetic fields, and where they cross, those fields twist into cosmic whirlpools. When magnetic field lines snap and reconnect, a process that unleashes solar flares on the sun, they could trigger FRB-scale explosions in these intersections. The sheer volume of plasma might amplify the signal, turning what would be a faint crackle into a deafening cosmic shout. Evidence: some intersection-linked FRBs show unusual polarization, their radio waves twisted as if they've spiraled through a magnetic labyrinth. But the wildest possibility: these FRBs might be tracing something even more exotic: dark matter annihilation. If dark matter particles cluster densely at filament junctions, their occasional collisions could release bursts of energy detectable as FRBs. It's a long shot, but if true, these brief flashes would be our first glimpse of dark matter's hidden interactions. Whatever's causing them, one thing's clear: these intersection FRBs aren't just cosmic static. They're screaming clues about the most extreme environments in the universe, places where the Webb's invisible architecture comes to life in spectacular, unpredictable ways. And with every new burst pinned to a filament crossing, the mystery deepens, pulling us further into the cosmic web's electrifying secrets. Somewhere in the tangled strands of the cosmic web, time stands still. While most of the universe's gas has been forged and reforged in the furnaces of stars, astronomers have stumbled upon something extraordinary: pristine pockets of hydrogen and helium lingering in filaments, untouched by the chaos of stellar birth. These aren't just clouds of gas, they're cosmic time capsules, preserving conditions from the universe's first billion years like bubbles of ancient air trapped in amber. The mere existence of these relics defies expectations. After 13.8 billion years of cosmic evolution, how could anything remain so unchanged? The answer lies in the Webb's quietest corners. Most gas in the universe gets tangled up in the messy business of galaxy formation, collapsing into stars, getting blasted by supernova, or ionized by the fierce radiation of quasars. But filaments, especially those far from the dense knots where galaxies cluster, offer a refuge. Their vast, diffuse structures can shield gas from shocks and radiation, leaving it cold, neutral, and chemically primitive. The best-known example, a filament near the quasar Ulysses J-ON 342+09, where spectroscopic analysis revealed gas nearly free of heavy elements, a fingerprint of the primordial universe. Finding these pockets is like digging up a fossil still breathing. Unlike the cosmic microwave background, which shows us the universe's infancy in faded light, this gas lets us sample the raw ingredients of creation directly. Its temperature, density, and even its motion carry clues about the universe's expansion rate in its youth, the strength of early gravitational waves, and the possible influence of exotic dark matter. Some of these filaments even exhibit deuterium levels, a rare isotope of hydrogen, that match predictions from Big Bang nucleosynthesis with uncanny precision. It's as if a laboratory from the universe's first minutes survived intact, hidden in plain sight. Yet the real mystery isn't just their preservation, it's their scarcity. Simulations suggest far more of this primordial gas should have survived, especially in the Webb's outermost tendrils. So where did it all go? One theory blames cosmic ultraviolet background radiation. a pervasive glow from early stars and quasars that might have ionized much of the gas, breaking apart neutral hydrogen atoms. Another possibility is that turbulence within filaments, stirred by passing galaxies or dark matter substructure, heated the gas just enough to prevent it from collapsing into detectable clumps. The hunt for these time capsules is pushing telescopes to their limits. Instruments like the extremely large telescope's Higher spectrograph, set to come online in the next decade, will scan filaments for the faint absorption lines of neutral hydrogen, tracing its distribution with unprecedented precision. Meanwhile, radio arrays like the Square Kilometre Array aim to map the cosmic web in 3 dimensions, revealing where primordial gas might still lurk. But the stakes go beyond curiosity. If these pockets are as pristine as they seem, they could hold answers to cosmology's biggest questions. Did dark matter's peculiar properties shield them from destruction? Do they hide traces of hypothetical particles from the universe's first seconds? Every untouched wisp of gas is a silent witness to epochs we can only simulate, and their survival against all odds hints that the cosmic web's quietest threads might be its most revolutionary storytellers. At the smallest scales imaginable, the universe seethes with chaos, a frothing sea of virtual particles popping in and out of existence so quickly we'd never notice. This quantum foam, as physicists call it, is the turbulent foundation of reality itself. But what if that microscopic frenzy didn't stay small? What if the cosmic web's filaments are nothing less than quantum fluctuations from the Big Bang, stretched to unimaginable sizes by the universe's explosive expansion? It's a wild idea, one that blurs the line between the infinitesimal and the infinite, suggesting that the universe's largest structures might be magnified echoes of its tiniest moments. The hypothesis hinges on inflation, the theory that the universe underwent a brief, exponential growth spurt in its first fraction of a second. During this violent stretching, quantum fluctuations in the primordial foam would have been blown up from subatomic scales to cosmic proportions, becoming the seeds for all future structure. In most models, these seeds grew into galaxies and clusters through gravity's slow pull. But the quantum foam hypothesis takes it further, proposing that filaments themselves might preserve the exact pattern of those early quantum ripples, like a photograph of the universe's first heartbeat enlarged to galactic dimensions. Evidence is elusive but tantalizing. When astronomers map filaments, they find strange correlations in their shapes, twists, and knots that mirror the fractal complexity of quantum foam simulations. Some filaments even exhibit peculiar density variations, as if their underlying structure retains the statistical fingerprints of those primordial fluctuations. The most striking alignment comes from the cosmic microwave background, where temperature variations believed to stem from quantum noise show clustering patterns eerily similar to modern filament distributions. It's as if the universe stamped its smallest fluctuations onto its largest canvases. Critics argue this is coincidence, a trick of statistics in a vast, messy cosmos. After all, gravity and dark matter should have reshaped filaments dramatically over billions of years, erasing any quantum signature. Yet proponents counter with an audacious possibility. What if dark matter is the quantum foam? Some theories suggest dark matter particles might be relics of that early froth, their unique properties preserving quantum patterns even as ordinary matter clumped into galaxies. If true, filaments could be literal snapshots of spacetime's quantum origins, frozen in dark matter's invisible grip. The implications stagger the imagination. If filaments encode quantum fluctuations, studying their shapes might reveal secrets about the universe's birth that no particle collider could ever reproduce. Are filament junctions the amplified collisions of primordial particles? Do their wispy tendrils trace the paths of ancient quantum entanglement? The questions multiply faster than answers. But the wildest thought of all, if this hypothesis holds, we're not just studying the universe's structure, we're glimpsing the quantum code from which it was built, written in filaments so vast they make the Planck scale look infinite. It's a reminder that the cosmic web might not just connect galaxies, it could bridge the very smallest and largest scales of reality itself. When you think of the cosmic web, you probably picture a chaotic tangle of filaments twisting uneven rivers of matter stretching haphazardly across the void. But look closer and something strange emerges. Some filaments aren't messy at all. They're perfectly balanced, aligning in eerie, symmetrical patterns that defy the randomness of gravitational growth. It's as if some cosmic draftsman took a ruler to the universe, sketching straight lines and mirror-like reflections into the fabric of space itself. Take the axis of evil, an infamous alignment of galaxy clusters and filaments spanning billions of light years, all mysteriously oriented along the same plane. This isn't just a fluke. Statistical analysis shows the odds of such symmetry arising naturally are less than 1 in 1,000. Even more baffling, the same axis aligns with the cosmic microwave background's largest fluctuations, as if the universe's earliest whispers somehow dictated this precision billions of years later. Then there's the cosmic train wreck, a trio of massive filaments in the Abell 2626 cluster that intersect at near-perfect 60-degree angles, forming a geometric honeycomb in the sky. Gravitational collapse shouldn't produce such clean symmetry, yet there it is, staring back at astronomers like a cosmic rebuke to their models. So how does randomness sculpt something so precise? One theory points to primordial magnetic fields, threading through the infant universe like invisible wires, guiding gas into unnatural order. Another idea suggests these symmetries are relics of an early universe phase transition, like cracks forming in ice as it freezes, leaving behind a hidden lattice. But the wildest possibility, these patterns aren't accidents at all. Some theorists speculate they're evidence of a deeper structure, perhaps even a shadow universe imprinting its geometry onto ours. Until we solve the riddle, these symmetrical filaments stand as silent monuments to a universe far more ordered and far stranger than we ever imagined. Black holes aren't just lurking at the centers of galaxies, they're on the move, and the cosmic web's filaments, they're the ultimate superhighways for these gravitational monsters. Recent studies reveal something astonishing. Supermassive black holes don't just sit quietly in their host galaxies. They travel, and when they do, they prefer the well-worn paths of filaments, riding these invisible rivers of dark matter and gas like cosmic commuters. This isn't just a curiosity, it could rewrite how we understand galaxy evolution itself. Take the case of the black hole in galaxy CID 42. This behemoth, weighing in at millions of solar masses, was caught red-handed fleeing its host galaxy at speeds topping 2 million miles per hour. At first, astronomers assumed it had been kicked out by a violent merger, but when they traced its path, they found something even more surprising. The black hole was perfectly aligned with a nearby filament, as if it had hitched a ride on an invisible track. Similar discoveries followed. In the galaxy cluster Abell 85, multiple supermassive black holes were found strung along a single filament like pearls on a necklace, all drifting away from their original homes. How does this happen? It all comes down to gravity's delicate dance. When galaxies collide, their central black holes can merge, recoiling from the gravitational waves unleashed in the process. But instead of drifting randomly through space, these ejected giants get funneled into filaments, the densest regions of the cosmic web. Like a marble rolling down a groove, a black hole follows the gravitational trough of a filament, its path steered by the dark matter and gas concentrated there. Simulations show this migration isn't rare. Up to 40% of wandering black holes could be following these hidden roads, their journeys spanning hundreds of millions of years. But the real shock is what this means for galaxies. If black holes routinely leave their hosts, it could explain why some galaxies, especially small ones, lack the supermassive black holes our models predict. More startling still, these traveling black holes aren't passive hitchhikers. As they barrel through the web, they can trigger star formation in the gas-rich filaments, ignite quasars in unrelated galaxies, or even strip gas from their surroundings, leaving behind cosmic deserts. Some researchers speculate that these rogue black holes could be the seeds of future galaxies, their gravity pulling in enough material to birth entirely new systems far from their original homes. The implications stretch even further. If black holes preferentially move along filaments, their distribution could map the cosmic web structure better than any telescope. Future gravitational wave detectors might even catch the ripples from their mergers, tracing the web's outline through spacetime itself. But the biggest question remains: how many of these dark travelers are out there, silently coasting along filaments, reshaping the universe one gravitational nudge at a time? Every new discovery peels back another layer, revealing a cosmos far more dynamic and far stranger than we ever imagined. Dark energy is the universe's great mystery, an invisible force pushing galaxies apart at an ever-increasing pace. But here's the twist: it might not be acting uniformly across the cosmos. While we often picture dark energy as a cosmic tide, evenly stretching the fabric of space, filaments could be telling a different story. Recent observations suggest these vast threads of the cosmic web might be resisting dark energy's pull in ways that voids and galaxy clusters aren't. It's as if the universe's expansion has a hidden loophole and filaments are exploiting it. Take the Pisces-Cetus supercluster complex, one of the largest known filament structures. Measurements show its expansion rate lags behind surrounding voids by a small but statistically significant margin. At first glance, this makes no sense. If dark energy's repulsive force is truly uniform, all large-scale structures should accelerate equally. Yet filaments seem to cling tighter to their shape, as if their dense concentrations of matter and dark energy are locked in a quiet tug-of-war. Some theorists argue this could be gravity's last stand, the combined pull of galaxies, gas, and dark matter within filaments fighting back against expansion just enough to slow it down. But there's a wilder possibility. What if dark energy itself behaves differently inside filaments? Quantum field theories suggest dark energy might interact weakly with matter, its strength varying based on local density. In the sparse emptiness of voids, it could dominate unimpeded, but in the crowded neighborhoods of filaments where matter piles up along megaparsec scale seams, dark energy's repulsive push might weaken like a spring compressed under weight. If true, this screening effect would mean the cosmic web isn't just shaped by dark energy, it's actively reshaping how dark energy works. The evidence is still tentative but tantalizing. Surveys like eBOS have mapped filament velocities, revealing subtle discrepancies in how fast they're moving apart compared to voids. Meanwhile, simulations that incorporate variable dark energy models produce filament networks eerily similar to the real thing, something uniform dark energy struggles to replicate. Yet skeptics counter that cosmic variance, random fluctuations in structure, could mimic these signals. After all, the universe is under no obligation to be perfectly uniform. The stakes: if filaments truly modulate dark energy, it would upend our understanding of cosmic fate. Instead of a lonely, frozen future where galaxies vanish over the horizon, the universe might retain pockets of structure longer than predicted, with filaments acting as cosmic anchor points. It's a reminder that even the most dominant force in the universe might not be as simple as we thought, and that the cosmic web's delicate threads could be hiding the keys to the cosmos's ultimate destiny. Neutrinos are the universe's ultimate ghosts, tiny, nearly massless particles that slip through planets like they're not even there. Trillions pass through your body every second, leaving no trace. But here's the cosmic irony: despite their ability to ignore almost everything, neutrinos seem to have one unexpected aversion: filaments of the cosmic web. When astronomers map the paths of high-energy neutrinos from distant astrophysical sources, they find something bizarre. these particles appear to steer clear of the densest threads of the web, as if the universe's largest structures cast invisible shadows. This isn't just a quirk, it's a direct challenge to our understanding of how particles interact with the cosmos on the grandest scales. The first hints of this anomaly came from IceCube, the neutrino observatory buried deep in Antarctic ice. While studying neutrinos from Blazar's supermassive black holes firing jets directly at Earth, researchers noticed a peculiar mismatch. The neutrinos' arrival directions didn't align with known filaments, even though those cosmic threads should be dense with matter. Statistically, the odds of this happening by chance, less than 1 in 1,000. It's like throwing darts at a map and having every single one land in the oceans, missing all the continents. At first, scientists assumed observational bias, maybe the instruments were missing something. But as more neutrino sources were mapped, the pattern held. Even more puzzling, this avoidance isn't universal. Lower energy neutrinos, like those from the Sun or supernova, pass through filaments unimpeded. Only the highest energy neutrinos, the ones born in the most violent cosmic events, seem to shy away. So what's blocking them? One radical idea involves dark matter's hidden interactions. If filaments contain dense clumps of exotic dark matter particles, they might scatter high-energy neutrinos, diverting their paths just enough to create these apparent shadows. Another theory points to quantum gravity affects microscopic warps in spacetime at energies so high, they alter how neutrinos travel across cosmic distances. There's even speculation that neutrinos might interact with magnetic fields threaded through filaments in ways we haven't yet imagined, bending their trajectories like light through a prism. But the most unsettling possibility, this could be the first clue that neutrinos aren't as indifferent to matter as we thought. The standard model of particle physics insists they barely interact with anything. Yet if filaments, with their unique mix of gas, dark matter, and magnetic fields are somehow visible to neutrinos, it might mean there's a new force or particle at play, one that only shows up at scales broader than galaxies. Every new neutrino detection adds another piece to the puzzle. Some trace back to empty voids as expected. Others seem to skirt filament edges as if repelled by an unseen barrier. And a rare few plunge straight through, defying the trend entirely. The inconsistency is maddening and thrilling, because if we can decode why the universe's most aloof particles suddenly develop preferences, it might crack open physics in ways we can't yet predict. For now, the neutrino shadow puzzle remains one of cosmology's quietest rebellions, a subtle hint that even the most untouchable particles might be whispering secrets about the cosmic web's hidden architecture. And until we listen closely, those whispers will keep drifting through the dark, just out of reach. Deep in the cosmic web's labyrinth of filaments, the universe might be humming a tune too low for our ears to hear. Not a literal sound, space's vacuum carries no waves for traditional microphones, but something far stranger. A resonance of gravitational waves or exotic particles vibrating through these vast threads like plucked strings on a celestial harp. This hypothetical cosmic hum isn't just background noise. It could be the echo of the universe's most violent events, or even the whisper of physics beyond our current understanding. The idea isn't as far-fetched as it sounds. Gravitational wave detectors like LIGO have already proven space-time ripples exist, capturing the crashes of black holes and neutron stars. But those are the cosmic screams, short, sharp bursts of energy. The hum would be different, a persistent, ultra-low-frequency vibration, perhaps from supermassive black holes orbiting each other for millennia before merging, or from the cosmic web itself oscillating as galaxies slide along its filaments. The catch, these waves could have wavelengths spanning light years, making them invisible to current detectors. It's like trying to sense ocean tides with a teacup. The scale is all wrong. Then there's the dark matter angle. If dark matter particles interact even faintly, their collective motion through filaments might generate a subtler hum, a sea of weakly interacting massive particles, WIMP, or actions sloshing through the web's channels, emitting faint signals as they go. Some theories suggest these particles could decay into photons or other particles at predictable rates, creating a diffuse glow or radio signal woven into the filament structure. The problem: this emission would be drowned out by the universe's cacophony of other radiation, like trying to hear a whisper in a hurricane. The hunt for this hum is pushing technology to its limits. Proposed detectors like the Laser Interferometer Space Antenna LISA aim to catch low-frequency gravitational waves by placing 3 spacecraft millions of kilometers apart, forming a triangle precise enough to measure space-time distortions smaller than an atom. Other projects like pulsar timing arrays use neutron stars as natural metronomes. Their ultra-regular pulses should stagger if long-wavelength gravitational waves stretch the space between them and Earth. Already, these arrays have detected a potential background rumble, though whether it's from the cosmic web or other sources remains unclear. What makes the hum so tantalizing isn't just its existence, it's what it could reveal. A gravitational wave hum might encode the merger history of supermassive black holes, tracing how galaxies grew along filaments over billions of years. A dark matter hum could unveil particle properties no collider can reach, and if the signal doesn't match predictions, that's when things get thrilling. An anomalous hum might hint at cosmic strings, hypothetical defects in spacetime from the universe's birth, or even extra dimensions vibrating beyond our perception. For now, the Cosmic Webs song remains just out of earshot, a melody woven into the dark. But as detectors grow more sensitive, we might soon tune into the universe's oldest rhythm and discover the filaments aren't just structures, but instruments in a symphony we're only beginning to hear. What if the cosmic web isn't just our universe's structure, but a scar from something far older and stranger? Among the filament's most perplexing patterns are irregularities so bizarre they've sparked a radical idea. These threads might bear bruises from collisions with other universes. Imagine 2 soap bubbles brushing in a froth of realities. Where they touch, the membranes distort. Could filaments hold similar imprints, cosmic fingerprints left by a multiverse we can't yet see? Take the cold spot, that eerie cosmic bruise we explored earlier. While supervoids might explain part of its chill, some theorists suggest an even wilder origin, a collision with another universe's gravitational pull warping our own. The math is speculative but tantalizing. In multiverse theories like eternal inflation, neighboring bubble universes could occasionally bump, transferring energy at their boundaries. A particularly violent collision might leave behind a void within a void, stretching filaments like taffy and imprinting unnatural temperature variations. The cold spot's edges even show faint hints of polarization patterns resembling those predicted for such an event, as if space itself still remembers the impact. Then there's the alignment problem. Certain filaments, like the Hercules Corona Borealis Great Wall, stretch far beyond predicted limits, clustering in ways that defy cosmological expectations. String theory offers a provocative explanation. These too big structures might trace the wake of a parallel universe grazing ours long ago, its gravity knitting matter into unnatural alignments as it passed. It's like finding a straight road through a forest. Nature rarely builds with such precision without a nudge. Even the filament's ghostly glow could fit this puzzle. If another universe's quantum fields briefly leaked into ours during a collision, they might have left behind exotic particles or energy signatures. These remnants could theoretically decay into the faint X-ray and UV emissions we now detect, like embers from a fire that burned across dimensions. The Lyman alpha forest's patchiness might even reflect this. Some regions of the web ionized not by local quasars, but by radiation bleeding through from the other side. Of course, skepticism runs deep. Many scientists argue these anomalies could stem from mundane cosmic variants or gaps in our simulations, After all, the multiverse is famously untestable, its fingerprints always just out of reach. But here's where filaments offer a unique opportunity. Their sheer scale makes them potential amplifiers for multiverse effects too subtle to spot elsewhere. A collision's gravitational waves, for instance, might resonate through filaments like a tuning fork, leaving distortions in galaxy motions or gas temperatures that future telescopes could catch. The wildest twist: if filaments do encode multiverse clues, decoding them might not require new physics, just better maps. Projects like the Euclid Space Telescope aim to chart the cosmic web in unprecedented detail, hunting for statistical oddities in filament shapes or densities. Even a single, inexplicable filament kinked at the wrong angle or vibrating with impossible regularity could hint at forces beyond our universe's borders. Whether these ideas hold up or collapse under scrutiny, one thing's certain: the cosmic web is more than a backbone for galaxies. It's a canvas where the universe, or perhaps universes, paints its boldest mysteries. And if even one filament bears the mark of a reality beyond our own, it would redefine not just where we are, but what everything truly means. The hunt for the universe's missing baryons has become one of modern astronomy's most frustrating detective stories. For decades, scientists have known the cosmic ledger doesn't balance. Roughly half the ordinary matter predicted by Big Bang nucleosynthesis simply isn't where our telescopes can see it. The leading suspect, hot gas laced through the cosmic web's filaments, so diffuse it's effectively invisible. But even with cutting-edge tools like the E-Rosetta X-ray telescope, this phantom material continues to evade capture, revealing just how cunning the cosmos is at hiding its secrets. Enter the warm, hot intergalactic medium, WIM for short. This theorized plasma, hotter than the sun's surface but spread thinner than Earth's best laboratory vacuums, should account for most of the missing baryons. The problem: its very nature makes it nearly undetectable. WIM doesn't glow brightly like stars. It barely whispers in X-rays, emitting just 1 photon per cubic meter every 1,000 years. Spotting it is like trying to find a single lit match in a foggy football field. That's where E-Rosetta 7 X-ray eyes come in. Scanning the sky with unprecedented sensitivity, this German-Russian space observatory doesn't look for WIM directly. Instead, it hunts for shadows, subtle dips in the X-ray light of distant quasars as their radiation filters through filaments. Recent E-Rosetta data from the Able 3391 and Able 3395 clusters revealed tantalizing hints. Between these galactic titans, astronomers detected a faint absorption line matching the fingerprint of oxygen ions, a telltale sign of million-degree gas threaded through the connecting filament. But here's the catch: the signal was 50 times fainter than predicted. Where's the rest? Some theorists argue the WIM might be clumpier than simulations suggest, with dense knots hiding most baryons while leaving vast stretches nearly empty. Others propose the gas could be cooling into an even stealthier phase, ultra-cold molecular hydrogen or exotic plasma states that evade current detection methods entirely. The plot thickens when you consider time. WIM isn't static, it's a dynamic fluid swirling through the web's gravitational currents. Shock waves from colliding filaments or outbursts from supermassive black holes might heat patches unpredictably, making them briefly visible before they vanish again into the cosmic background. This could explain why some observations, like those from the Chandra X-ray Observatory, catch flickering filaments that disappear upon deeper inspection. It's as if the universe is playing a shell game with its baryons, moving them just as we zero in. Yet the biggest surprise came from combining X-ray and ultraviolet data. When the Hubble Space Telescope examined the same filaments E-Rosetta probed, it found ultraviolet absorption lines, but not where the X-rays suggested. This mismatch implies the WIM isn't uniform at all. Instead, it might exist in multiple layers, blistering outer sheaths detectable in X-rays, wrapped around cooler cores visible only in UV. If true, the missing baryons aren't so much missing as they are masquerading, their full mass only revealed when viewed through every wavelength at once. The implications stretch beyond inventory. If WIM's structure is this complex, it could rewrite how galaxies form. Current models assume filaments feed galaxies with smooth gas flows, but these patchy, turbulent reservoirs suggest growth spurts and famines, cosmic droughts followed by downpours of star-forming fuel. Even dark matter's role comes into question. Could its gravitational tug be stirring the WIM into these elusive configurations, or might dark matter particles interact with the gas in ways we've yet to imagine? Every new observation peels back another layer, but the core mystery endures. With upcoming missions like Athena and Lynx poised to join the hunt, we're closer than ever to solving this cosmic accounting error. Until then, the missing baryons remain both a testament to our ingenuity and a humbling reminder. The universe excels at hide and seek, and we've only just begun to learn its tricks. Among the most baffling residents of the cosmic web are ultra-diffuse galaxies, ghostly, sprawling structures that defy every expectation of how galaxies should look and behave. Take Dragonfly 44, a celestial spectre drifting in the Coma cluster. At first glance, this galaxy appears almost empty. Its stars spread so thin you could fly through it for thousands of light years without spotting a single sun. Yet despite its wispy appearance, Dragonfly 44 moves with the gravitational confidence of something far more substantial. Measurements reveal a dark matter halo nearly as massive as the Milky Way's, a staggering contradiction for a galaxy with just 1% of our galaxy's starlight. This mismatch isn't just peculiar, it's revolutionary. Standard galaxy formation models insist that visible starlight should roughly trace a galaxy's dark matter content. Dragonfly 44 flips that logic on its head, proving dark matter can pile up in near-total isolation, like an invisible mountain range no one thought to map. The implications ripple outward. If galaxies can be this dark matter-dominated, our entire framework for how cosmic structures grow might need recalibrating. Some researchers speculate these ultra-diffuse galaxies are failed giant objects whose gas was stripped away by violent encounters early in cosmic history, leaving behind dark matter skeletons with only a whisper of stars. Others propose they're relics of an era when dark matter clumped differently, forming pockets where gravity sculpted galaxies into these eerie, stretched-out forms. But Dragonfly 44 isn't alone in its defiance. Consider NGC 1052DF2, another ultra-diffuse oddity in the M96 group. This galaxy isn't just faint, it's almost entirely devoid of dark matter, a discovery that sent shockwaves through astronomy when confirmed in 2018. Its stars move sluggishly, unburdened by the gravitational anchor most galaxies rely on, as if someone forgot to pack the universe's most abundant ingredient. The existence of such dark matter-free outliers throws another wrench into the works. If ultra-diffuse galaxies can form with or without dark matter, what chaotic processes govern their birth? The cosmic web's role in this mystery can't be overstated. Most ultra-diffuse galaxies cluster near filament intersections, where dark matter flows converge like rivers meeting a delta. Yet instead of bustling with star-forming activity as simulations predict, these regions spawn these ghostly, quiescent objects. One leading theory suggests filaments might act as cosmic filters, stripping gas from smaller galaxies through relentless tidal forces while leaving their dark matter halos intact. Alternatively, the web's magnetic fields or shock waves could inhibit star formation, creating galaxies that never quite ignite. What makes these faint giants so vital is their potential to reveal dark matter's true nature. Their extreme environments, whether overflowing with dark matter or suspiciously lacking it, serve as natural laboratories for testing exotic theories. Could their dark matter be fuzzy, composed of ultra-light particles that spread out differently than traditional models predict? or do they hint at unforeseen interactions between dark matter and ordinary atoms? Every new ultra-diffuse galaxy discovered adds another piece to the puzzle, each one whispering secrets about the invisible scaffolding holding our universe together. The deeper we look, the stranger the picture becomes. Recent surveys have uncovered ultra-diffuse galaxies with bizarre internal structures, some hosting globular clusters far too large for their diminutive frames, others rotating in ways that defy gravitational logic. Whether cosmic accidents or dark matter's most telling footprints, these ghostly islands force us to confront a humbling truth. The universe crafts galaxies in ways we're only beginning to comprehend, and the cosmic web might be hiding its most revolutionary blueprints in the faintest ink imaginable. The faint glow emanating from the cosmic web's filaments might not just be the last gasp of ordinary matter, it could be the death rattle of something far more exotic. While shock-heated gas and turbulent magnetic fields explain part of this ghostly luminescence, astronomers are chasing even stranger possibilities, including the spine-tingling idea that dark matter itself might be disintegrating within these cosmic threads. Imagine particles that have existed since the universe's first second, lurking invisibly for billions of years, finally meeting their end in the filament's depths, their decay sparking flashes of light like cosmic fireflies. One leading candidate, sterile neutrinos, hypothetical, heavier cousins of the neutrinos we know. Unlike their detectable siblings, these shadowy particles could make up dark matter, clustering in filaments where their occasional decays would emit X-rays. The European Space Agency's XMM Newton telescope has even spotted unexplained X-ray emission lines near filament junctions, matching predictions for sterile neutrino decay. If confirmed, this would solve two cosmic mysteries at once, the nature of dark matter and the source of the web's eerie glow. But skeptics argue these signals could also come from mundane sources like hot gas or pulsars, leaving the neutrino hypothesis tantalizingly unproven. Then there's the black hole evaporation theory, an idea ripped straight from Stephen Hawking's notebooks. Primordial black holes, those hypothetical relics of the Big Bang, might pepper the cosmic web like knots in a rope. If they're small enough, think asteroid-sized, quantum mechanics dictates they'd slowly leak energy via Hawking radiation, their final moments releasing bursts of gamma rays and X-rays. Filaments with their dense concentrations of dark matter would naturally trap these ancient black holes, making them ideal hunting grounds for such evaporation signals. Japan's Hitomi satellite glimpsed a flicker of excess soft X-rays from the Perseus cluster's filament, a whisper that could match a swarm of evaporating mini black holes. Yet without repeated detections, the claim remains controversial. But the wildest explanation of all, action's ultra-lightweight particles theorized to solve a quantum puzzle in particle physics. If they exist, actions could decay into pairs of photons inside filaments, creating a diffuse glow across multiple wavelengths. The twist, these particles might also interact weakly with magnetic fields, meaning the web's immense magnetic tendrils could focus their decay light into bizarre polarized patterns. Recent observations from the Hubble Space Telescope revealed filament regions with unexpected ultraviolet polarization, a fingerprint action models predicted. What makes these exotic possibilities so electrifying isn't just their audacity, but their testability. Each leaves distinct spectral signatures future telescopes like NASA's upcoming Lynx X-ray Observatory could confirm or rule out. A sterile neutrino decay would show up as a specific energy spike at 3-5 kiloelectronvolts. Action glow would polarize light in telltale spirals and evaporating black holes. Their death throes should spark unpredictable, high-energy flashes, cosmic fireworks lighting up the web's darkest corners, yet the implications run deeper than detection. If dark matter decays in filaments, it means this invisible substance isn't eternal, it's slowly eroding, transforming the cosmic web structure over trillion-year timescales. Filaments could thin or even disconnect as their dark matter skeleton dissolves, reshaping the universe in ways our simulations never anticipated. Meanwhile, primordial black holes evaporating en masse would inject energy into the web's gas, potentially reheating material that should have cooled billions of years ago. For now, the filament glow remains a riddle wrapped in an enigma, a signal that could rewrite particle physics, reveal dark matter's identity, or expose entirely new cosmic phenomena. Every flicker, every unexplained photon carries the potential to overturn our understanding of the universe's hidden architecture. And until we decipher its true source, these luminous threads will keep haunting the edges of our knowledge, whispering secrets from the darkest corners of physics. Simulations of the cosmic web paint a serene picture filaments as tranquil rivers of gas, patiently feeding galaxies over billions of years, but reality is far more violent. New research reveals these threads might be under constant assault, their gas blasted away by the very stars they helped create, the culprits, supernova stellar explosions so powerful they can sculpt the cosmos on scales we're only beginning to comprehend. Take the case of a single massive star reaching the end of its life. When it detonates as a supernova, the explosion unleashes energy equivalent to 100 billion nuclear bombs, ejecting debris at 10% the speed of light. Multiply this by millions of stars in a galaxy cluster, and you've got a cosmic hurricane, a relentless gale of high-energy particles and shock waves capable of stripping gas from entire filaments. Advanced simulations, like those run on the Frontier supercomputer, show how these cumulative winds create vast bubbles in the surrounding gas, pushing it outward like a snowplow clearing a street. Over time, these bubbles merge, forming colossal cavities where filament gas should be. But here's the twist: this isn't a one-time event. Galaxies experience repeated bursts of star formation, each wave spawning new supernovae that compound the damage. The Illustris TNG simulation, one of the most detailed models of cosmic evolution, tracks this process over 13 billion years. Its findings are startling. Up to 40% of a filament's gas can be displaced by these winds, not just temporarily but permanently. The expelled material doesn't gently settle back. It's hurled into the voids between filaments, lost to the intergalactic wilderness. The aftermath looks eerily like real-world observations. In the filament connecting the Virgo and Coma clusters, astronomers have spotted vast, asymmetrical gaps in the gas distribution regions where simulations predict supernova winds would carve their deepest trenches. Even more telling, the gas that remains often shows abnormal metal enrichment, a fingerprint of supernova debris mixing back into the filament like ash stirred into a river. This pollution alters the gas's cooling properties, potentially stunting future star formation in ways we're only beginning to understand. Yet not all filaments suffer equally. Dense, thick threads like those near galaxy clusters resist disruption, their stronger gravity holding the gas in place. It's the thinner, more delicate filaments that bear the brunt of the damage. The spiderweb filament, a wispy structure in the distant universe, appears riddled with holes in ALMA telescope data, as if celestial buckshot has torn through it. Simulations suggest such fragile threads might never recover, their gas forever scattered, leaving behind skeletal dark matter frameworks devoid of stars. What makes this phenomenon so pivotal is its ripple effect. If supernova routinely drain filaments of their gas, they're not just altering local structures, they're throttling the universe's ability to build new galaxies. Future star formation depends on fresh gas deliveries along these cosmic highways, and every lost atom is a missed opportunity for stellar birth. Some theorists argue this could explain why the universe's star-forming peak occurred billions of years ago. Supernova might have systematically starved filaments, turning down the spigot of galactic growth. But the story isn't entirely bleak. These same winds might also seed future complexity. Blown-out gas, enriched with heavy elements from supernova, could eventually cool and collapse into new, metal-rich structures, perhaps even triggering the formation of ultra-diffuse galaxies or rogue star clusters in the void. It's a cosmic cycle of destruction and rebirth, written in the fading glow of filament gas and the echoing fury of long-dead stars. The deeper we probe, the clearer it becomes. The cosmic web isn't a passive scaffold. It's a battleground shaped by forces as violent as they are creative, and every missing pocket of gas tells a story of stars that lived fiercely, died explosively, and in their passing reshaped the universe itself. Imagine the universe as a vast, chaotic dance, galaxies swirling, filaments twisting, and voids stretching in every direction. Yet within this cosmic frenzy, astronomers keep stumbling upon something that defies randomness, eerie, perfect symmetries. Filaments that align like soldiers in formation, vast structures mirroring each other across billions of light-years, patterns so precise they feel deliberate. How can something born from the primordial turbulence of the Big Bang end up looking like it was drafted by a mathematician? The debate boils down to two possibilities. Either these symmetries are flukes, cosmic variants masquerading as order, or they hint at something deeper, a fundamental structure woven into the fabric of spacetime itself. The cosmic variance camp argues that given enough randomness, even a universe as vast as ours will occasionally produce coincidental alignments. Throw a handful of confetti, and eventually a few pieces will land in a straight line. But critics counter that the odds are worse than winning the lottery back-to-back with a blindfold on. Take the axis of evil, that infamous alignment of galaxy clusters and filaments spanning nearly the entire observable universe. Statistical analyses suggest the chance of such a perfect arrangement happening randomly is less than 1 in 1,000. Enter the cosmic microwave background, the universe's oldest light. Its temperature fluctuations, tiny variations imprinted when the cosmos was just a toddler, show a peculiar preference for the same axis as modern filament alignments. It's as if the universe's first whispers somehow dictated where its largest structures would form billions of years later. Could inflation, the universe's explosive growth spurt, have stretched quantum fluctuations into these vast, unnatural symmetries? Or is there a hidden hand at work, something beyond our current physics? Future surveys like Euclid and the Vera Rubin Observatory aim to settle the debate. By mapping millions of galaxies and filaments in unprecedented detail, they'll test whether these symmetries hold up or dissolve into statistical noise. If the patterns persist, it could mean rewriting our understanding of cosmic structure formation. Some theorists even speculate that these alignments might be scars from a multiverse collision, like wrinkles left on a bedsheet after a restless night. Yet the most tantalizing clue might come from magnetism. Filaments threaded with large-scale magnetic fields could act as cosmic guide wires, shaping gas flows into unnatural order. Simulations show that if primordial magnetic fields were strong enough, they might have combed the early universe's chaos into the eerie symmetries we see today. But here's the catch: no one knows how such powerful fields could have arisen in the first place. Whether fluke or fundamental, these symmetries force us to confront a humbling truth. The universe might be far more orderly or far stranger than we ever imagined. And until deeper surveys peer into the web's hidden architecture, these perfect alignments will remain cosmic riddles, taunting us with their precision. From vanishing matter to spinning filaments, from ghostly galaxies to collisions with other universes, each of these 25 cosmic riddles peels back another layer of the universe's greatest illusion. We thought we understood the cosmic web as a simple scaffold, a passive backdrop to galaxies. Instead, it's a living, breathing enigma, defying the laws we wrote to explain it. Dark matter clumps where it shouldn't, filaments glow with no clear power source, entire galaxies drift in isolation, untouched by the threads that should have birthed them. Even the most fundamental forces, gravity, electromagnetism, behave differently inside these vast strands. as if the universe plays by different rules in its darkest corners. Yet for every answer we chase, the cosmos tosses back another question. Why do some filaments spin while others lie still? How can structures grow larger than physics allows? What hums in the spaces between galaxies, particles we've yet to name, or echoes of dimensions we can't see? The more we map the web, the more it feels like a hall of mirrors reflecting our own ignorance back at us. But here's the thrilling part. We're on the verge of breakthroughs that could rewrite the story. The James Webb Space Telescope peers deeper into filaments than ever, hunting for the faintest whispers of primordial gas. LISA, the Gravitational Wave Observatory, might soon tune into the hum of colliding supermassive black holes along these threads, tracing the web's vibrations like a cosmic stethoscope. And observatories like the Vera Rubin Observatory are scanning the sky nightly, poised to catch flashes from phenomena we haven't even dreamed up yet. So stay curious, because the cosmic web isn't just a mystery, it's an invitation. An invitation to question, to explore, to admit how much we still don't know. And somewhere in those tangled threads between the glow of dark matter and the whispers of ancient light, the next great discovery waits, not just to fill gaps in our maps, but to shatter the maps entirely and send us searching anew. The universe's greatest story is still being written, and you've got a front row seat.